This is Heba Amir. I'm a PhD student at Hasselt University, and I will be presenting the paper Expressiveness within Sequence Datalog. It's a joint work with Jan Hedders, Jan Paradens, and Jan van den Bussen. Just from the title of the presentation, it's clear that we focus on sequence data. And to be specific, we focus on sequence databases, which are the databases that allow the management of collections of sequences. And this means that relations then hold tuples of sequences of atomic values. As a motivating example related to genomics, consider the case where we have three organisms, A, B, and C, and we want to check whether there is a gene in C that has a substring with its prefix coming from relation A and its suffix coming from relation or organism B. It's clear that querying these databases will require extra features, and our goal then is to obtain a thorough understanding of the role that the different language features play in querying sequence databases. So in our research, we chose to work with Datalog for so many reasons. An important one is that adding sequences in Datalog is not a new invention. So Datalog for sequence databases, our Sequence Datalog, was already introduced and studied by Bonner and Mecca, but in the research, they focused on studying different problems. To show the ingredients of Sequence Datalog, I will be doing this with examples. As a first example, consider the following program. Looking at the program, you will find like that. Dot is the concatenation symbol. What begins with an @ symbol is an atomic variable, while what begins with a $sign is a path variable. Moreover, epsilon is the empty path. And before going through the program, notice that both relations R and S are unary, so each one of them is a set of paths, while T is a binary relation. Thus, it's a set of pairs of paths. Also note that in all of our examples, S will always be the output predicate, so the output of the query on some instance will always be the sequences in S after evaluating the program on this instance. The program computes a query queue that returns the reversals of the path in R. So for each path in R, we create a tuple in T that holds the value of that path in its first argument, while the second argument is set to the empty path. We recursively remove the last atomic value from the first argument and add it to the end of the second argument. Eventually, we reverse the original path when the first argument becomes empty, and this is what we select to put in S. In addition to this setup, we have a very special operator which we call packing. So packing is denoted by these angular brackets. You can think of packing as an operation that encapsulates or pack a path. It's also a way of constructing new path, and it can be used as a delimiter for parts of path. A packed value is the packing of some path. So packed values have a nested definition as they are defined in terms of path, which is defined in terms of packed values. That's why in the example, we have a packed value inside a packed value. It's also worth mentioning that an atomic variable cannot have a packed value as its value. As an example to motivate the operation of packing, consider a tree with root label A. This tree has n children, where each of the children is a tree itself. If you want to represent the whole tree by a single path, we can easily do this with the help of packing. We can recursively pack each child and concatenate all of the children trees packings to the label of the root. As another sequence data log example that contains packing, consider the following program that checks whether there are at least 3 different occurrences of strings from relation A as substrings in the strings from the relation R. So what we do is the following. For each substring of a string in R that belongs to relation A, we create a path in T for that string, but with that substring being marked by replacing it with its packing. The query returns true then if there are at least 3 different paths in the relation T. And now to begin our research, we need to define precisely the features we have in Sequence Datalog. And to illustrate the different features, I'll be using the 2 programs I have just showed you. So we have 6 features in total that can be used by a program, and you can just memorize them with their initials by the 2 words air and pin. The first one is A, which is arity. So we say that a program uses arity or has the A feature if it contains at least one predicate of arity greater than 1. The reversals program we have seen before is an example of a one that uses arity, since T here is a binary predicate. The second feature is I, or intermediate predicates, which is used by a program if it involves at least 2 different IDB relation names. The same example also uses intermediate predicates, since we have T and S as IDB predicates. Next, R, recursion, which is well understood. And from the example above, we have the predicate T, which is defined recursively. Next, P, packing. And we say that packing is used by a program if a path expression of the form packing of some other expression occurs in some rule. The substrings program uses this feature in the head predicate of the first rule. The next feature is E, equations, and a program uses this feature if it contains at least one equation between path expressions in some rule. The program has three negated equations. Last but not least, N, negation, and this is also well understood. And again, here the program uses negation with the three equations. Having these features defined, and in order to measure the expressiveness of the different features and evaluate how they affect each other, our methodology is to develop what is a sequence data log fragment and what we mean by subsumption. So, a sequence data log fragment is a subset of the set that contains the six features. And we say that a program is in some fragment if it uses only the features in this fragment. It does not have to use all of them though. Then we say that a fragment F1 is subsumed by another fragment F2 if and only if every query computable by a program in F1 is also computable by a program in F2. And to really measure the power of the features, we wanted to avoid some superficial results like packing is primitive because we have to output packed values, for example. So we wanted a class of queries that does not require the use of any of the features. Thus, we focus on what we call monadic flat queries, where monadic means that the arity of the input and the output relations is at most 1, and by flat we mean an instance that does not have pegged values. So the queries we are interested in, when evaluated on flat instances, the result of the query is then guaranteed to be flat as well. Next, I give one example of a query that can be expressed in different fragments. Consider the query A's only, which returns the path in R that consists only of A's. The first program computing this query belongs to the fragment IEN. It basically filters into the sequences in R that have at least one atomic value not equal to A. And then it selects the sequences in R that are not in T. So what we do is that we try to see if we can express the same query in different ways. And one surprising way is by a program that uses only equations. The equation in the second program makes sure that the variable x contains only a's. And you will notice that the two programs used equations. So can we do it without equations? And yes, this is possible by the third program, which uses arity, intermediate predicates, and recursion. So we first create two copies of the path in R and save them in T. In the second argument, we recursively eliminate the last atomic value only if it's an A. We then output only the path which appear in the first argument of T with an empty second argument. So E doesn't seem essential, but we introduced arity and recursion instead of it. So can we do it without arity, for example? And the answer again is positive. With the help of packing in program 4, we can simulate arity and use it as a kind of a delimiter between the two arguments. This hack seems to be working with any program that uses arity. So this means in our notions that arity is redundant in the presence of packing. Going back to program number 3, we said that we introduced recursion in order to eliminate equations. So can we compute the same query without equations and recursion at the same time? And the answer again is positive. The fifth program is in fragment AI, but here we used arity. So lastly, in program 6, we can compute the query using only intermediate predicates. So the question now, can we do it without any of the features? And if you looked carefully to the 6 programs, you will find that at least I or E was needed. And we actually show in the paper that this query is not expressible without the features either I or E. And we use that to prove that equations are primitive in the absence of I. So if we cannot use intermediate predicates, then equations cannot be simulated in general. And to make this more precise, we have defined different notions of redundancy and primitivity of features. We can have that a feature is redundant or primitive in an absolute sense, or in the presence and or absence of other features. Having said this, I will briefly mention the results for packing as it's the most involved proof. So our results show that packing is redundant in an absolute sense. So we can simulate packing without the use of any of the other features. And to do this, we have to consider two different cases. The first is in the presence of recursion, and the second is in the absence of recursion. In the recursive case, we can build on an old result for a PODS 2017 paper that introduced a sequence data log language to query JSON. For the non-recursive case, the main challenge in this proof is to be able to eliminate packing from equations in rules. So in order to do that, we found that it's quite similar to the problem of solving word equations, where words are strings over variables and constants. The variables in the case of word equations are similar to our Paul variables, and the constants are our atomic values. The problem is to get the solution set of unifiers that make the two words identical. So we leverage this technique by adding packing and atomic variables to the algorithm and argue why we guarantee termination in our case. The following diagram is a summary of all of our results. With this Hasse diagram, we have a complete view of the results, which shows the relative expressiveness of each fragment. Using the diagram, we can check whether a fragment F1 is subsumed by another fragment F2 by checking if there is an ascending path in this diagram going from F1 to F2. So an ascending path denotes subsumption, while the absence of such a path denotes non-subsumption. And how we determine whether there is a path in the diagram from one fragment to another or not is by our primitivity and redundancy results. So subsumption is showed by redundancy results. On the other hand, non-subsumption is showed by primitivity results. And if you looked carefully at the diagram, you will notice the following. We have classified 11 equivalence classes that are made up of 16 different fragments, where some fragments have been proven to be equally expressive, such as I and E. Also, you will notice that arity and packing are not mentioned at all because our results show that they are completely redundant. Another remark is that negation and recursion are entirely primitive. Even with the power added by sequences and equations, we still could not simulate recursion. And last but not least, our results show that equation and intermediate predicates can simulate each other when no recursion or negation is used, but intermediate predicates are strictly more expressive than equations when combined with negation or recursion. So to conclude the talk, I will only show in the next slide some points among many that are interesting to be investigated in the future. By that, I end my talk and thank you so much for listening.